Hi, everyone, and welcome to page 5 of the practice exam. This is the mechanism page. We're told to draw the structure of 1s2r, 1-bromo, 2-methyl cyclohexane. So let's start with that. That's 1 and that's 2. So we have a bromine on 1 and a methyl group on 2. We want to make sure that carbon 1 is of an S configuration. If we were to start by drawing this as a wedge, we would notice that our prioritization would go, I'm going to get rid of these numbers. Our prioritization would go 1, 2 over here because that's connected to a methyl group, and 3, the hydrogen's pointed back. So this would actually be an R configuration. So instead, what we do is we draw a dash, and that's going to make it S. We want to make the methyl group carbon, or the one that has the methyl group here, we want to make this R. So if we were to, let's just not draw the line, let's just say this would be priority 1. Down here would be priority 2, the methyl group would be priority 3, and then there would be that invisible hydrogen would be priority 4. So if you go around and count the circle, 1, 2, 3, it's going counterclockwise, or S. So we want to make sure to flip that by making that one dashed as well. So now it looks like S, but it's actually R because that hydrogen is coming out. We're looking at it in the wrong way. So it's actually R. And that's just drawing the first part. We're told that it reacts with sodium hydroxide, and it gives a complicated mixture of products, a lot of different ones. The products observed have molecular formulas of C7H14O. So you can see that the little notes here that the bromine leaves. Oxygen is new, right? There's a new oxygen in there. Whereas in the second one, we have a C7H12. So actually oxygen didn't get incorporated. We simply just lost the bromine, and some other stuff is happening there too. Something that actually would be really helpful to do is to draw the molecular formula here, because that'll help us figure some other fun things out. There's 7 carbons total. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 hydrogens and 1 bromine. So you'll notice, to get even more specific, over here, we gained a new hydrogen. So it's actually the OH group that's new. And then over here, it looks like we actually lost a hydrogen as well. Those are going to be some nice, simple things that you can check for without really knowing anything about the mechanisms just yet. So we're going to draw the mechanisms for both products, noticing that hydroxide could act as a base and as a nucleophile. We're going to work on the first one where the oxygen is incorporated. So again, the bromine leaves and the OH is new. So let's just go ahead and situate that OH group right here just to see what happens. And it's pretty tempting to do this, but we want to be very careful before we do that. We want to make sure we go through all of our steps to determine whether it's SN1 or SN2. So here we go. Secondary carbon, so it could be SN1 or SN2. This is where we look at the solvent. The solvent is water. That's pretty darn protic. It stabilizes a carbocation, so it favors an SN1 reaction. So it's a good thing that we thought about that before moving on. The first step is actually the bromine leaving on its own. We have a secondary carbocation intermediate, and that one right there is a chiral center that is fixed because it is unaffected by that reaction. Now we could have the OH group, the hydroxyl group, come in and do its nucleophilic attack. And I'm going to do it like that, just so you can see that it actually starts from the oxygen and ends at the carbon. The product is then cyclohexane. We have this carbon here, and this is a newly formed chiral center, but it's a mixture of R and S, which works out really well for us because we were given this other hint that our product should be a mixture of diastereomers. So this right here is a mixture of the R and the S compound. So that's our first part. I went ahead and just copied that structure right up above. The next part that we're going to focus on, so we can ignore this for a second, we took care of the fact that hydroxyl could act as a nucleophile. Check. So let's show how this could act as an electrophile. brackets in between here before I get too ahead of myself, and I'll label that as SN1. All right, so we're going to have actually a pretty similar starting point. We're going to have a secondary bromide methyl group here. Just kidding, we're not going to have a similar starting point. Got ahead of myself. All right, so our stuff is a nice, very, very strong base. And having that strong base there is really going to dictate that it's an E2 reaction. Because in an E2 reaction, the very first thing that happens is a base picks up the beta proton, beta being one carbon away from the bromide. So the carbon connected to the bromide is in the alpha position, and this is the beta position. Now, rather than alpha beta, it's sometimes called 1 2. So 1 2 1 2. Either way, that's the general relationship, and I'm going to just minimize how many numbers we have. So we're going to take a look and see where our protons are in, I don't know if I said this explicitly, but this is going to be now an E2 mechanism. And the thing to keep in mind for stereochemistry of an E2 reaction is that the setup between our leaving group and our proton has to be anti-periplanar, which is a fancy way of saying that the bromine's got to be on the opposite side of the hydrogen that it's leaving with. So as you can see, we have two options for how it could leave. It could leave with the hydrogen that's over here and trans or opposite side of the ring to the bromine, or anti-periplanar, or it could leave with this one here. And it's going to go for the tertiary hydrogen because that's going to give the more highly substituted alkene product. So we're going to focus on that proton. We'll have the base, a strong base, come in, pick up the hydrogen. These two electrons get kicked over to make that alkene, the double bond, and the bromine leaves. And that's consistent with our initial notes that we should be losing a bromine and a hydrogen. The product that we get is then this alkene, and don't forget about that methyl group there. This is now sp2 or flat, so there's no more stereochemistry at that carbon. Here we go, just redraw our C7H12 product. Bonus question, unexpected product. Same molecular formula observed. The unexpected product is a constitutional isomer, so it still has the same molecular formula, different connectivity. It's not a stereoisomer, but it's due to a rearrangement of the reaction intermediate, and that's consistent with what we had here, that we had, once again, an actual carbocation intermediate, as opposed to an SN2 reaction that does not have an intermediate. The beginning of this is going to be exactly the same as what we had above in the SN1 type reaction. We have this bromine methyl group, but the bromine leaves on its own. We're in a protic solvent that's going to stabilize that. We have a secondary carbocation that's next to a tertiary carbon, and we have a hydrogen here. And that hydrogen could participate in a hydride shift, where these two electrons from the hydrogen kick over, not to the bond, but they kick over to the carbon. So the hydrogen moves and brings its electrons with it. Sorry about that, I hit the table. This is known as a hydride shift. Hydrogen moves with its electrons. So now we have an extra hydrogen on this carbon here, it's just a CH2 group. That's still tertiary carbocation. All this time, hydroxide has been waiting around for its chance to party. And here it is, finally ready, now that we have the more substituted tertiary carbocation. It's ready to attack. We have no more chiral center, so we don't really have to worry about stereochemistry so much, but this is going to be our other product, that tertiary alcohol. And that's the bonus question. That's this page. Thank you for watching.